have the second half of 1.4, which covers intermediate value theorem, squeeze theorem, and continuity. Intermediate value theorem shows up quite a bit, so we need to for sure make sure that you can do that one. Okay, so our requirements today: understand and use intermediate value theorem, understand the squeeze theorem, and then use properties of continuity to make an interval continuous if it was not already continuous. Our homework is over there on the right, pages 80 to 81. So first off, some properties of continuity. So what are these properties? So if we know that the functions f of x and g of x are continuous at a point, so like x equals c, then we also know that these functions are continuous at c. So we can do a scalar multiple. A scalar is just multiplying by some constant number, so it's like a coefficient. So if we know that x squared is continuous, which it's continuous everywhere, it's a parabola, you never have to pick up your pencil to draw it, then you could just toss a number in front of it, like a 3. 3x squared will also be continuous. All right, well, the next one, sum and difference. If we know that x squared is continuous, because it's a parabola, and we know that x is continuous, because it's just a straight line, we could also say that x squared minus x is continuous. So we could bring that together. And we could say that f of x plus g of x would be continuous. So either way there. Products work as well. If you have x squared and you have x and you multiply them together, two different functions multiplied, then its product, which would be x cubed, would also be continuous. Quotients work as well. X squared over x, well, that's the same thing as just x. It is continuous as well. On the bottom, the composition f of g. Okay, so f of g would be something like, if this is f, x squared plus 1, and this is g, let's do x minus 3, then f of g would mean that we rewrite this outside function with x minus 3 here inside of the x. So let's do that. We will do x squared plus 1, and inside of the parentheses, we'll put x minus 3. Okay. If we were to multiply out x minus 3 times x minus 3, we would end up with x squared minus 6x minus, plus 9, and then plus the 1 off on the end, and this whole thing would turn into x squared minus 6x plus 10. So this function would be continuous at c if the original functions were also continuous at x equals c. Right. So it's just kind of like, if you know that both functions are continuous, you can do pretty much anything with them with properties. You can do what you want. Next thing is intermediate value theorem. This is one of the first theorems that we actually have to get memorized. But memorizing the idea behind it is just as good as memorizing the words. Okay, so first off, if f is continuous on the closed interval from a to b. All right, that one's not so bad. Let's draw in a and b down there on the bottom. Here is a, and here is b. Okay. We can tell from this order that the a is first, so it's going to be the lesser x value, and b is second, so it's going to be the larger or greater y or x value. Okay, so these are x values. Okay, we know it's closed interval, and for something to be continuous on a closed interval, that means that the endpoints need to be actually at the ends of your continuous function. Okay, so no arrows pointing straight up, so no like vertical asymptotes, and no holes at A and B or anywhere in between. Okay, let's say that K is any number between f of A and f of B. All right, so what does this mean? F of A is the y value when x equals a. So let's just make a point for that. Let's make this right here f of a. And let's put b down here, but it could be above or it could be at the same height. It doesn't really matter, but that's going to be f of b. Okay. And then we can just kind of draw something because we know that this is a continuous function. Okay, there's lots of options though. It doesn't have to like move down. It could have moved up. It could have done a weird wave, kind of whatever. It could have been like a V shape. Lots and lots of options. Okay. So I'm going to use orange now. K is going to be a number between f of a and f of b. So that means that K is a y value between f of a and f of b. So I'm going to put K, how about here? It does not have to be exactly in the middle, it just has to be between somewhere. Then there is at least one number C in A to B. So that means that C is an X value as well. It's an X value, where C is between A and B, such that f of C equals K. So the Y value, where X equals C, the Y value is K. We kind of work this backwards though. We start with K, and then we look over here to see, aha, here is the point between A and B, right? There's the point where the Y value is K. So really we just need to find out what the X value is. So that is C. Okay, so C is between A and B if K is between f of A and f of B. And it does not matter if f of A or f of B is on top there. So the intermediate value theorem proves existence. It proves that there has to be some number here if there's a K value in between f of A and f of B. However, it does not mean that there is only one X value with the Y value of K. Let's do an example like that. So let's have A, B here again. And let's have B over here. And I'll just kind of keep f of B in the same general spot. So this is f of B. And let's put f of A in kind of the same general spot as well, f of A. Okay. The difference of what I'm going to do here is I'm going to draw a different picture. So instead of just like smoothly moving down and then just kind of bumping back up, I'm going to move down considerably and then up considerably and then back down. All right. K is still going to be a Y value in between f of B and f of A. But if you notice this time, a whole bunch of points, 3 points in fact, have the same Y value. So that means that down here and here and here, those are 3 different options for C. So that's why it says at least one over here. It's possible that there's more than one C value. So I'm going to name these C1, C2, and C3. This example is a super common way to use the intermediate value theorem, which is often abbreviated IVT, intermediate value theorem. It applies to the indicated interval, so it tells us between 0 and 3, and we want to find the value of C guaranteed by the theorem. So C is that X value. Okay. It tells us over here that f of C equals 0, so that is our Y value. So really what this question is asking is what X value between 0 and 3 gives us 0 as the y value. What x value between 0 and 3 gives us 0 as the y value. All right, so how do we test that, huh? Well, what we really need to figure out is what are a and b, and what are f of a and f of b. We got to figure out what those endpoints are so that we can then like kind of draw in between. We're not actually going to draw it, but we're going to kind of get the idea of it in our minds. So let's start with a. I've been doing a in green. A is the first x value here. So if our x value is 0, we want to find out what is f of 0. And we find out f of 0 by plugging in 0 for x here and here. Doing that math out, we would get 8. Okay, and then let's do b. b is going to be the second x value in that closed interval. So that's going to be f of 3 will be the y value for that. So f of 3, let's see, 3 squared is 9, minus 3 times 6 is 18. So 9 minus 18 is -9, and -9 plus 8 is -1. Okay. So what these two bits right here represent are the points 0, 8, and 3, -1. Okay. So this says verify that the intermediate value theorem applies. So that is the first bit that we are going to do. So we're going to stop here, verify that this applies. That means we're going to go up here to the actual theorem. It says if f is continuous on a closed interval. So is f actually continuous on the closed interval from a to b? So let's look at f of x. Are there any discontinuities? Are there any spots where like a denominator would equal 0? Any spots where you've got like a square root of some weird stuff? The answer to that is no. This is a polynomial, so it is continuous. So we're going to start with because f of x is continuous, CTS for continuous, on, and then we're going to do the closed interval from 0 to 3. Okay, so we're basically just rewording this whole thing to go with our numbers. Instead of like a and b, we get to use like 0 and 3. Okay. And k is any number between f of a and f of b. All right. So k, they gave us a k, that y value, that f of c. So 0 is between f of a and f of b. Is 0 between those? Is that y value in between the two y values that we got? Yes. And 0 equals k, right? That's our k value, is between. Then I'm going to put f of 0 equals 8, and f of 3 equals -1, right? 0 is between 8 and -1. Backwards, but yeah, it totally works. Okay. Then there exists a c. Then there exists a c between 0 and 3, where f of c equals 0 by the intermediate value theorem. Okay, so we've shown how that's going to work. It's going to look something like this. F of 0 is 8. F of 0 is 8, like up here. F of 3 is -1. So somewhere in between those two endpoints, there's going to be the y value of 0. We just have to figure out actually what that spot is. And I don't know if it's 1.5, kind of like what I did. Let's find out. Okay. So what we have done so far is verify that the intermediate value theorem applies to the indicated interval. Cool, we're done with that. Okay, that's the sentence. The second half of this is find the value of c that the theorem guarantees. So there's got to be a point. There's got to be an x value in between 0 and 3 to get a y value of 0. So what we're going to do is say the y value, so it's going to be like k equals, and then you put f of x, like your actual function. Okay, this is how you'll set up every single one of these. K was the y value they gave you, which was 0 in this case, and that's going to equal the original function, which was x squared minus 6x plus 8. Usually this is going to be a number that's not 0, but 0 does show up sometimes. So it could have been like 4 equals and then all of this stuff. Okay. How do you solve this then? We want to get x by itself. Well, this is x squared, it's a quadratic, so we got to get everything on one side of the equals. There's a 0 over here, so we don't have to subtract or add anything to both sides. Looks like we are going to factor on the right-hand side. So 0 equals, looks like x, minus 2, x minus 4. And then you set each one of your factors equal to 0. So x minus 2 equals 0, x minus 4 equals 0. So that means that x equals 2 and x equals 4. Both of those numbers would make our original function have a y value of 0. However, only one of these guys is on our interval. So 2 is between 0 and 3. So that means that's a less than sign. So that means that c has to equal 2. This is not on the interval. All right, so we have just shown what c equals. Okay, so the last little bit, why do we care about the intermediate value theorem? What's the whole purpose of this? Well, if we know that a function is continuous and that the function has positive and negative values of f of x, so that's talking about y values. If there's positive and negative y values, then we can conclude that somewhere f of x equals 0. Okay, so there's got to be some y value of 0 as long as our function is continuous and has some positive and some negative f of x values.